Ever feel like you're drowning in data? Like there's just so much information out there these days.
Yeah, definitely. Happens to me all the time, especially when I need to get up to speed on some new technology, for like a meeting or something.
Yeah. Or even just for my own curiosity.
Right. Like, how do those massive systems, the ones running behind the scenes of like everything we do online, how do
Yeah.
they actually work?
Well, that's what we love to dig into here.
Exactly. And today's deep dive is into a system that's a real heavy hitter, Cassandra. It's all about storing structured data, and it was born at Facebook.
Oh, wow. Facebook, huh?
Yeah. And the stuff you sent over, it really gets into the nuts and bolts of Cassandra, like why it was even created, how it's designed at its core, and what problems it's meant to solve.
Sounds like a fascinating deep dive. It is. We've got this presentation that walks us through basically everything. The initial motivation behind Cassandra, the way it models data, how it organizes information, and its architecture, plus the nitty-gritty of how it's implemented from a tech perspective. There's even a section on how Facebook used it for their inbox search, which is pretty cool.
So are we going to see how it stacks up against other database systems? I'm always curious about those comparisons.
Absolutely. The presentation touches on that, and it even gets into some of the bigger questions surrounding NoSQL databases in general.
Nice. Big picture stuff.
So our mission, and by listening, you've already accepted it, is to distill the essence of Cassandra. We want to understand why it exists, what makes it unique, and ultimately give you, the listener, a rock-solid grasp of this important technology.
And we'll do it without getting lost in the technical weeds, right?
Absolutely. No jargon overload, promise. Ready to dive in?
I'm all set. Lead the way.
Okay, so first, let's set the stage. Cassandra's origin story is pretty interesting. It wasn't some abstract concept. It was born out of a very specific need at Facebook.
Ah, so a real-world problem they had to solve. Makes sense.
Exactly. The presentation states that Facebook created Cassandra specifically to handle the enormous, and I mean enormous, storage demands of their inbox search feature.
Facebook inbox search. Wow. Yeah, I can only imagine the amount of data flying around there.
Yeah.
So what was the main challenge? Storage capacity.
It seems so. Think about the sheer volume of messages, attachments, all that stuff. They needed a system that could handle it all.
And I'm guessing it had to be super reliable too, right?
Absolutely. But here's an interesting tidbit. The presentation actually points out that for Facebook's inbox, the occasional bit of slightly outdated information was less of a concern than having the system go down entirely.
Ah, so they were willing to trade a little bit of perfect consistency for the sake of keeping things up and running.
It seems that way. And this all happened a while back, by the way. The source mentions Cassandra was open sourced to Apache in 2008, so it's got some history behind it.
2008, huh? That's before a lot of the NoSQL stuff really took off, right?
Yeah, Cassandra was definitely one of the pioneers in that space. And the version we're looking at in this presentation is 2.1.0, which gives us a snapshot of where it was at a certain point in time.
Makes sense. Okay, so Facebook needed a solution for this huge inbox search problem, and that's where Cassandra came in. What were the driving forces behind its design? What were they aiming for?
Well, the presentation highlights three key pillars: high scalability, high availability, and high write throughput. Those were the non-negotiables.
Okay, let's unpack those. Scalability, we're talking about the ability to grow, right?
Yeah.
To handle more and more data as the system expands.
Precisely. And the source emphasizes linear scalability. That means that as you add more servers to a Cassandra setup, its capacity to handle read and write operations increases proportionally.
So basically, if you double the number of servers, you double the performance.
In an ideal scenario, yes. That kind of scalability is incredibly powerful for a company like Facebook dealing with, billions of users.
Yeah, it's like if you need to handle more email, you just add more servers to the system. Pretty straightforward.
Exactly. Then there's high availability. This is all about resilience, making sure the system stays up and running even when things go wrong. And the source is very clear about this. Cassandra is designed with the expectation that failures will happen.
Oh, interesting. So it's not like, oh, we hope nothing breaks. It's more like things will break, so let's be ready for it.
Exactly. It's a system that embraces failure as a normal occurrence, not some rare exception that's baked into its DNA.
And that makes a lot of sense when you think about it. If you have hundreds or even thousands of servers, something is bound to go wrong at some point.
Right. A hard drive fails, a network connection drops, whatever. Cassandra is built to keep chugging along, even when some of its parts are down.
Very cool. Okay, and the third pillar, high write throughput, that's about how fast it can ingest new data, right?
Exactly. Like, for Facebook's inbox, new messages are constantly pouring in. The system needs to be able to record that information quickly and reliably. And the presentation mentions two key factors that contribute to this. An efficient disk access policy, meaning it's optimized for writing data to storage, and flexible consistency levels.
Flexible consistency levels. Now that sounds interesting.
It is. It basically allows you to fine-tune the trade-off between absolute data accuracy across all copies and achieving even higher performance and availability.
Okay, I'm starting to see how these different design goals play together.
Now, the presentation also brings up this concept called the CAP theorem, which is kind of a fundamental principle in distributed systems.
Ah, yes, the CAP theorem. I've heard of it, but a refresher would be great. How does Cassandra fit into that?
Well, the CAP theorem basically says that in any distributed system, you can only strongly guarantee 2 out of 3 desirable properties:
Which,
consistency, availability, and partition tolerance. Consistency means that all parts of the system have the same up-to-date view of the data at all times. Availability means that the system is always responsive, ready to handle requests. And partition tolerance means that the system can continue to function even if the connection between different parts is disrupted, like if there's a network issue.
okay, so you can only pick 2 out of those 3. You have to make a trade-off.
Exactly. And Cassandra, as the source explains, is an AP system. It prioritizes availability and partition tolerance.
So it's all about staying up and running and handling requests, even if there might be brief moments where some parts of the system haven't fully synced up on the latest data.
Precisely. It's a conscious decision to prioritize keeping the service alive and kicking, even if that means you might occasionally see slightly older information before everything catches up.
Got it. So it's eventual consistency rather than immediate absolute consistency across the board.
Exactly. And the presentation contrasts Cassandra with CP systems. Those prioritize consistency and partition tolerance, and also with another AP system called Dynamo.
Dynamo, right? That's Amazon's thing, isn't it?
It is. So both Cassandra and Dynamo fall into this AP category, but the presentation highlights a key difference between them:
What's that?
their data models. It boils down to how they structure and organize information. Cassandra is described as column-oriented, whereas Dynamo is a key-value store.
Column-oriented versus key value.
Hmm.
I'm not sure I fully grasped that.
Well, in simple terms, a key-value store is pretty straightforward. You have a unique key, and it directly points to a chunk of data. Think of it like a dictionary.
Okay, key value pairs. I get that.
Okay.
Column-oriented.
In column-oriented systems like Cassandra, data is organized into columns, and then those columns are grouped into families.
So it's kind of like a table, right, with rows and columns.
Sort of, but it's more flexible than a traditional table in a relational database. Each row is still uniquely identified by a key, but different rows can have entirely different sets of columns.
Ah, so it's like each key points to a collection of columns that are relevant to that specific piece of data.
Exactly. And the presentation briefly touches on Google's Big Table, which is also column-oriented. But unlike Cassandra, it falls into the CP camp, prioritizing consistency over availability.
Got it. So different systems, different trade-offs, different ways of organizing data.
Right. And the source gives us a glimpse into some of the techniques they use. Like, Big Table uses column families, in-memory tables called mem tables, and these sorted disk files called SS tables. Dynamo focuses on consistent hashing, partitioning data, and replication, all strategies for achieving their respective goals within that CIP theorem framework we talked about.
Okay, that gives us a good lay of the land. Now I'm ready to dive into the heart of Cassandra, the data model.
All right, let's do it. The presentation starts with this statement: a table is a distributed multidimensional map indexed by a key.
That's a mouthful. Can we break that down?
Definitely. Imagine a regular table, like you'd see in a spreadsheet or a database. You've got rows and columns.
Right, basic table structure.
In Cassandra, each row is uniquely identified by a key, just like in a traditional table. But here's where it gets interesting. Instead of every row having the exact same columns, it's more adaptable. Think of it like a map where each key can point to a collection of columns.
Okay, so different rows can have different sets of columns associated with them. That's flexible.
Exactly. And the multidimensional part just means that you can have lots of different columns associated with a single key. It's not limited to a fixed set of columns for every row.
Okay, I'm starting to see how that flexibility could be really useful.
And the distributed part just emphasizes that this entire structure, this table with its keys and columns, is spread across many different computers that are working together as a cluster.
No, right, so it's not all sitting on a single machine. That makes sense for scalability.
Precisely. The presentation also points out that operations are atomic on each row per replica. This is important for data integrity.
What does atomic mean in this context?
It means that when you make a change to a specific row, that change is applied consistently across all the copies, replicas of that row that exist on different servers. It's an all or nothing kind of deal.
So no partial updates or inconsistencies between different versions of the same row?
Exactly. And another key point, the values stored in these columns are basically strings sequences of characters, and there's no limit to how long those strings can be.
Wow, no size restriction. That's pretty powerful.
It is. It gives you a lot of freedom in terms of what kind of data you can store.
Okay, so we've got these tables, keys, columns, flexible structure. What's next in this data model tour?
The presentation then introduces column families, CFs. Think of these as containers for grouping related columns together within a table.
So instead of just a jumble of columns, you organize them into these families.
Exactly. And the source notes that you need to define these column families in advance, which gives Cassandra a certain degree of structure. It's not a completely free-for-all.
So it's structured, but still more flexible than a traditional relational database.
Right. Correct. It's a balance between structure and flexibility. And you can have tons of column families within a single table.
Okay, so how do I decide what columns go into which column family?
That's where your data modeling skills come in. You group columns based on how they're related to each other, how they're likely to be accessed together.
Right. It's about making it efficient to retrieve the data you need.
Exactly. Now, there's a distinction mentioned between two types of column families, simple and super.
Oh, simple versus super. I'm intrigued.
It's a bit of a nested structure thing. A simple column family is just a straightforward collection of columns. A supercolumn family is like a two-level hierarchy. It contains supercolumns, and each supercolumn then holds a collection of regular columns.
So it's like a directory with subdirectories and files.
That's a good analogy, but there's a caveat. In later versions of Cassandra, like 2.0, they actually got rid of supercolumns.
Really? Why did they do that?
It seems they were trying to simplify things, to move towards a more streamlined data model.
Makes sense. Complexity can be a killer sometimes.
So for the 2.1.0 version we're looking at here, supercolumns are still a thing, but it's good to keep in mind that they're not part of the picture anymore in newer versions.
Got it. So within these column families, we have individual columns, each with a name, a value, and a timestamp. That timestamp seems pretty important.
It's crucial. The timestamp helps Cassandra deal with situations where you have multiple updates happening to the same column at roughly the same time, maybe on different servers.
Ah, right, like if two people are editing the same document simultaneously.
Exactly. The timestamp tells Cassandra which update is the most recent, the one that should be considered the current value.
Smart. Keeps things in order.
And the presentation mentions that columns within a column family can be ordered either by their timestamp or by their name.
So flexibility in how you organize things within those families.
Exactly. And finally, the way you interact with this data model through the API is pretty straightforward. You've got insert, get, and delete operations.
Basic CRU'd operations, I'm familiar with those.
And the syntax for specifying which column within which column family you're working with, like column family. Column name, it's logical and easy to understand.
Cool. So we've got a good handle on the data model now. What's next?
Let's move on to the architecture, how this whole system is put together. The presentation breaks it down into 4 key areas: partitioning, replication, cluster membership, and bootstrapping.
Okay, let's start with partitioning. What's that all about?
Partitioning is the magic behind Cassandra's scalability. It's how the data is distributed across all those different servers, the nodes that make up a Cassandra cluster.
So it's like dividing up the responsibility for storing the data.
Precisely. And the source explains that Cassandra uses a technique called consistent hashing to achieve this.
Consistent hashing. I've heard the term, but how does it actually work?
Imagine all the servers in your Cassandra cluster arranged in a big virtual circle, a ring.
Okay, I'm picturing a ring of servers.
Now, consistent hashing uses a mathematical function, a hash function, to assign each server a specific position within this ring.
So each server gets a spot on the ring.
Right. Now, when you want to store a piece of data, the key associated with that data is also run through this hash function.
So the data gets a position on the ring too.
Exactly. And the server responsible for storing that data is the first one you encounter as you move clockwise around the ring from the data's position.
Okay, I'm starting to get it. It's like slicing up the ring into sections, and each server owns a certain slice.
You've got it. And that server, the one that owns the data based on its position on the ring, also becomes the coordinator for any operations related to that data.
That makes sense. Keeps things organized.
Now, the real beauty of consistent hashing, as the presentation points out, is what happens when a server joins or leaves the cluster.
Okay, so the cluster is growing or shrinking, new servers are added, old ones are removed. What happens to the data?
With consistent hashing, the impact of adding or removing a server is localized. It only really affects the servers immediately next to it in the ring.
So you don't have to reshuffle all the data across the entire cluster.
Exactly. That's a huge advantage over older, simpler ways of dividing up data.
Makes it much easier to scale the system up or down. But the presentation also mentions some potential issues with basic, consistent hashing. Something about uneven data distribution and not being aware of server load.
Right. One problem is that if you just rely on a basic implementation of consistent hashing, you might end up with some servers holding a lot more data than others, even if they all have the same capacity.
Ah, so it's not perfectly balanced.
It might not be. And another issue is that basic consistent hashing doesn't really take into account how busy each server actually is. Some might be underutilized while others are overloaded.
Okay, so those are definitely things you'd want to address.
Absolutely. And the presentation mentions two ways Cassandra tries to tackle these problems. One is through virtual nodes, or VNodes.
Virtual nodes, what are those?
Basically, instead of each physical server having a single position on the ring, you give it multiple virtual positions.
So it's like one server pretending to be multiple servers.
In a way, yes. It helps to spread the data more evenly across the ring.
I can see how that would help with balancing.
Now, Cassandra actually takes a different approach, as described in the source. It continuously monitors the load on each server and dynamically adjusts their positions in the ring to try and balance the workload.
So it's like a self-adjusting system, constantly trying to optimize things.
Exactly. It's more sophisticated than just a static, fixed assignment of positions based on hashing.
Very cool. Okay, next up, replication. We talked
Right.
about high availability. This must be how Cassandra achieves that one.
You're right on the mark. Replication is all about creating multiple copies of your data and distributing those copies across different servers.
Redundancy makes sense.
Exactly. The source states that data is replicated across n hosts, where n is the replication factor.
Replication factor, meaning how many copies you want to keep.
Precisely. And you can configure this replication factor based on your needs and your tolerance for risk.
So if I'm really paranoid about losing data, I could set a high replication factor, like, I don't know, 5 copies of everything.
You could. And the presentation then describes different replication policies: rack unaware, rack aware, and data center aware. These are different strategies for where those replicas are actually placed within your infrastructure.
Okay, so it's not just about how many copies you have, but where you put them.
Exactly. Rack unaware is the simplest approach. It takes the coordinator node, remember, the one that owns the data based on the hashing, and replicates the data to the next N1 servers in the ring, going clockwise.
So it just spreads out the replicas along the ring without really thinking about the physical location of those servers.
Exactly. Now, rack-aware replication is a bit smarter. It tries to distribute those replicas across different physical racks within a data center.
Racks, like those cabinets full of servers.
Exactly. So if you have a rack of servers and that entire rack goes down, you still have copies of your data on other racks.
Ah, so it's about protecting against bigger failures than just a single server going bad.
Precisely. And rack-aware replication usually relies on a coordination service like Zookeeper to figure out where to place those replicas.
Zookeeper, another one of those behind-the-scenes systems that makes everything work.
Exactly. Then you have data center-aware replication, which takes things even further. It aims to distribute replicas across geographically separate data centers.
Wow, so even if an entire data center is wiped out by, like, a natural disaster or something, you still have your data safe.
That's the idea. It's about ultimate redundancy and disaster recovery.
Makes sense, but it probably adds more complexity, right?
It definitely does. Managing replication across multiple data centers comes with its own set of challenges.
Got it. So different replication strategies for different levels of paranoia.
Exactly. And the diagram in the presentation showing rack-unaware replication makes it really clear how it just spreads out those copies along the ring.
Yeah, visually it's easy to grasp.
Okay, let's move on to cluster membership. This is about how all those individual servers, the nodes in a Cassandra cluster, know about each other and how they handle new nodes joining and existing nodes leaving.
So it's about maintaining awareness of who's in the club, so to speak.
Exactly. And Cassandra uses an interesting mechanism for this, an anti-entropy gossip protocol called Scuttlebutt.
Gossip, like spreading rumors.
In a way, yes. In network communication, a gossip protocol means that individual nodes periodically exchange little bits of information about themselves and about other nodes they've interacted with.
Okay, so they chat amongst themselves, sharing little tidbits.
And as this information spreads, eventually every node in the cluster gets a pretty accurate view of the overall state: who's online, who's joined, who's gone offline.
So it's like a decentralized way of keeping everyone in the loop.
Precisely. Now, what about that anti-entropy part of the name?
Yeah, that sounds interesting. What's the anti-entropy about?
It's basically a mechanism for making sure that all the replicas of a given piece of data eventually converge to the same correct value.
Ah, right, because remember, they're prioritizing availability. So you might have some replicas that are slightly out of sync for a bit.
Exactly. And anti-entropy is about fixing that. It's a background process where nodes compare their versions of the data and reconcile any differences that might have crept in due to network issues or temporary failures.
So it's like a constant cleanup crew, making sure everything is consistent in the end.
You've got it. And this gossip protocol is also used for failure detection, figuring out if a node has gone offline.
Makes sense. If a node stops gossiping, it's probably dead.
Well, it's not quite that simple. Cassandra uses a more sophisticated approach called accrual failure detection.
Accrual failure detection.
That sounds fancy.
It's a way of assigning a level of suspicion to each node based on how consistently it's responding to those little communication attempts, those heartbeats that are part of the gossip protocol.
Okay, so it's not just a binary alive or dead, but more like a sliding scale of, we haven't heard from you in a while, you're starting to look suspicious. Exactly. And the presentation notes that Cassandra was actually one of the first systems to use accrual failure detection in a gossip-based setup.
Cool. So they were innovating in that area.
They were, and they used an exponential distribution to model the changes in that suspicion level, which is a fancy way of saying they made it more responsive to actual failures while being less likely to mistakenly flag a healthy node as down.
So less prone to false alarms.
Okay.
Okay, what's next in the architecture rundown?
Finally, we have bootstrapping and scaling. Bootstrapping is the process for a brand new node joining the cluster for the very first time.
Ah, so it's like the onboarding process for a new server.
Exactly. When a new node starts up, it's assigned a random token, which determines its initial position in that virtual ring we talked about earlier.
Okay, so it gets its spot on the ring.
Right. And it saves that token locally, and depending on the replication policy, it might also register its presence with Zookeeper.
So it announces its arrival. Hey, everyone, I'm here. This is my spot on the ring.
Exactly. And then the crucial part. It starts participating in the gossip protocol, spreading the word about its existence and its assigned token.
Cool. So it integrates itself into the network.
Precisely. Now, scaling is about adding more capacity to a cluster that's already up and running, maybe because it's starting to get overloaded.
Okay, so you've got a busy cluster and you need to beef it up.
In that scenario, when a new node joins, it's given a token that's specifically chosen to help relieve the load on an existing overloaded node.
So it's not just a random assignment anymore.
All right, it's targeted to help balance things out. And then the overloaded node figures out which portion of its data now falls within the new node's range on the ring, and it copies that data over.
Oh, they share the workload, like good neighbors.
Exactly, and that boosts the overall capacity and performance of the cluster.
Awesome. Okay, I think we've got a pretty good grasp of the architecture now. It's all about intelligently distributing data, ensuring it's always available, and making it easy to grow the system as needed. Now, I'm curious about the implementation, the nitty-gritty details of how Cassandra actually stores and retrieves this data on disk.
All right, let's get into the technical guts of it. The presentation focuses on the core components of Cassandra's storage engine and the processes involved in writing and reading data.
Sounds good.
They highlight three key pieces: the commit log file, the mem table, and the SS table, sorted strings table.
Okay, let's break those down one by one. What's the commit log file all about?
Think of it as the first line of defense against data loss. It's described as an append-only file that resides on a dedicated local disk.
Append only, meaning you just keep adding new information to the end of it.
Exactly. And ideally, this disk is separate from the main storage disks for performance and redundancy.
So every write operation that comes into Cassandra is first recorded in this commit log.
Precisely. It's like a safety net. Even if the server crashes before the data can be written to the more permanent storage, it can be recovered from the commit log.
Makes sense. You don't want to lose any data, especially in a system like this where availability is paramount.
Now, the mem table is an in-memory data structure. There's one of these for each column family we talked about earlier.
Okay, so it's in memory, meaning it's fast to access.
Exactly. Once a write is safely recorded in the commit log, it's also placed in the mem table.
So it's like a temporary holding area for recent writes.
You've got it. And the data in the mem table is kept in sorted order, which makes it really efficient to find specific pieces of information.
Okay, so reads can be super fast if the data is in the mem table,
Yeah.
but it can't stay there forever, right?
You're right. Eventually, the mem table gets full, and that's when a process called flushing happens.
Flushing, like flushing a toilet.
Well, sort of. It means that the data in the mem table is written to disk, creating an S-stable assorted strings table.
Ah, okay. So the mem table is like a buffer, and when it's full, it gets flushed to disk as an SS table.
Perfect analogy. And these SS stables are sorted by key, which is important for efficient retrieval later on.
Okay, so over time, as more data is written and more mem tables are flushed, you end up with multiple SS tables on disk.
Exactly. And that brings us to compaction, another important background process that Cassandra runs.
Compaction. What's that about?
Think of it as a cleanup and optimization process. Compaction merges multiple SS stables together, combining their data and getting rid of any deleted or outdated records.
So it's like taking a bunch of messy files and consolidating them into a nice, clean, organized file.
Precisely. And it's important for performance because it reduces the number of SS stables that Cassandra has to look through when it needs to find a specific piece of data.
Makes sense. Fewer files to search through means faster results.
Now let's walk through what happens when you write some data to Cassandra and then later try to read it back.
Okay, so we're following the data's journey.
First, as we've discussed, the write goes to the commit log for durability, then to the mem table for quick access.
Got it. Write, log, mem table.
When you try to read that data back, Cassandra first checks the mem table. If it's there, great, super fast read.
Easy peasy.
But if it's not in the mem table, Cassandra has to go look for it in those SS tables on disk.
Which could be slower.
To speed up that disk lookup, each SS table has two helper structures, a Bloom filter and an index file.
Bloom filter. What's that?
It's a probabilistic data structure. Basically, it can tell you very quickly if a specific piece of data might be in a particular SS stable.
So it's like a quick check to avoid wasting time searching in the wrong place.
Exactly. And if the Bloom filter says, hey, this data might be here, then Cassandra uses the index file to pinpoint the exact location on disk where the data is stored.
Cool. So a two-step process to make disk reads more efficient.
The presentation also briefly mentions read repair. It's a mechanism for ensuring consistency across those replicas we talked about earlier.
Right, because we said that sometimes those replicas might be slightly out of sync.
Exactly. So during a read operation, if Cassandra detects that different replicas have different versions of the same data, it triggers a background process to bring them back in line.
So it's constantly working behind the scenes to keep things consistent.
It is. Now let's talk about how Cassandra handles all these different operations happening at the same time. It uses something called a staged event-driven architecture, or SETA.
That sounds pretty sophisticated.
It is. SETA is about breaking down the processing into stages, and each stage has its own queue, event handler, and thread pool.
Okay, so it's like an assembly line, where different parts of the process are handled by dedicated workers.
It's a good way to think about it. And the key advantage is that you can independently tune each stage, adjust the queue size, the number of threads to optimize for different types of work.
So you can have one stage that's really good at handling write requests, another stage for read requests, and so on.
Exactly. It allows Cassandra to juggle all those different tasks efficiently and achieve high overall performance.
Very cool. What about that commit log maintenance we saw in the presentation?
Right. So the commit log isn't just one massive file that grows forever. It's managed in segments.
So it's like splitting it up into smaller chunks.
Exactly. And each segment has a header that keeps track of which memtable data has been successfully flushed to the more permanent SS stables on disk.
Ah, okay. So it's like a checklist, marking off what's been safely stored.
Exactly. And that allows Cassandra to purge those older segments of the commit log once it knows the data is safe.
Makes sense. You don't want to keep unnecessary data around forever.
And the presentation wraps up the implementation section by listing the key modules within each Cassandra node: partitioning, cluster membership and failure detection, and the storage engine, all the pieces we've been discussing.
It's like seeing how all the parts fit together.
And it notes that Cassandra is implemented in Java, which is a popular programming language for large-scale systems, and that its architecture is based on this SETA model we talked about.
All right, we've covered a lot of ground. Background, data model, architecture, implementation. I'm ready to see how all of this comes together in a real-world use case. Facebook inbox search.
Let's do it. The presentation explains that there were two.